I'm Caitlin Lieberson, and this talk is called Lagrangian Realizations of Ribbon Cobordisms. All of this work is joint with John Entner. This is my cat, Aiko, who apparently is going to make an appearance. Yeah, so first of all, just to kind of spoil the whole result right at the beginning, basically the result is that every ribbon cobordism has a Lagrangian realization. And so I'm going to tell you, first of all, what kind of all of these things are as a quick recap, and then see how it is we know that this is true. Okay, so first of all, quick recap. The standard contact structure on R3 is just the two-plane field that's given as the kernel of a one form, in particular, the one form dz minus y dx. You can see it right here. Notice that as we go out from the origin in the positive y direction, the tangent planes or contact planes rather, are rotating up toward the vertical. And if you go out along the negative y-axis, they're rotating down toward the vertical. And if you notice any parallel copy to the y-axis in the xy plane, the planes look exactly the same. And if you look at any of one of these planes in here and just kind of translate up to a point, it'll be the exact same plane there. So that's what the two-plane field, this contact structure is describing is. And Legendrian knots are then just embeddings of circles into R3, which are actually everywhere tangent to the contact planes, meaning if you just take any point along your curve, it's going to be the curve is going to be tangent to the contact plane right there. Okay, so that's just a quick recap of Legendrian knots, but I was talking about Legendrian realizations. So one of the first things you might wonder is, does every smooth knot have a Legendrian representative? In other words, are there Legendrian knots that are smoothly isotopic to a given smooth knot? And it turns out, yes, there are. And in fact, there are actually infinitely many different Legendrian knots. So knots that are not Legendrian isotopic, but are smoothly isotopic to any given knot. So for an example, if we look at just the smooth unknot, it has infinitely many different Legendrian representatives. This is the max TB representative. Thurston-Benneken number gives us an invariant of Legendrian knots. It turns out this is one stabilization of it. Stabilization just means kind of adding zigzags. There are infinitely many other ones. You can think of adding more zigzags, for instance, as one way to see that there are infinitely many different Legendrian representatives of the same smooth knot. Okay, so the other thing I want to talk about, though, are ribbon cobordisms and Legendrian realizations of these, or some idea of a realization into contact symplectic world of that. As a quick reminder, a ribbon cobordism is just a properly embedded surface, let's call it C, and it's in the interval cross S3. Basically, the two boundaries are your two knots or links, and then it's just constructed by a sequence of these three moves. So you can have traces of isotopy. So any isotopy of a smooth knot gives you a ribbon cobordism between those knots, or links, I should say. You have births of unknots. So what I mean by that is if you have your knot here and you just add in an unknot, this is a zero handle attachment, that is another builds a ribbon cobordism, and we also have band moves, which I'll give you an example of in a second. So here's an example of a ribbon cobordism from the unknot to the mirror of 6-1. Notice that the first thing we have going on here is we have a birth. So we took this unknot and now we have a birth of a second unknot next to it. And then we just do a band sum. Notice that it's going to be a framed band sum. So if you take some curve that attaches two different unknots or the same component of your link and put some framing on it. In this case, I'm doing the Blackboard framing, in particular of this band. Then we'll see that we get this knot, which is the mirror of 6-1. And this movie gives us a way to build up a smooth concordance, actually, from the unknot to the mirror of 6-1. And this is an example of a ribbon concordance. Okay, so I was talking about kind of Legendrian, Lagrangian realizations of things. So we started out with, in the smooth world, we had smooth knots, and we saw that there were Legendrian representatives of these knots. In other words, Legendrian knots that were smoothly isotopic. to a given smooth knot type. And in fact, we saw that there are infinitely many of them. What John Etner in my result is saying is that if we start with ribbon cobordisms over here in the smooth world, then the analogous thing that fits over in the contact symplectic world is decomposable Lagrangian cobordisms. Okay, so recap of what these are. A decomposable Lagrangian cobordism between two Legendrian links, let's say from lambda 0 to lambda 1. It's exactly a Lagrangian submanifold in the symplectization of R3. So we take our standard contact structure on R3, which remember was the kernel of a 1 form. That's right here. And from that, we can build up a symplectic form manifold cross with another copy of R, let's call the variable on that RT, and then this gives us a symplectic form on the symplectization. And once we have that symplectic manifold, these Lagrangian cobordisms are just Lagrangian submanifolds of the symplectization. And one way of thinking about them as being is as being built up by these different moves. Notice that I'm saying decomposable ones. So the three moves for a decomposable Lagrangian cobordism are traces of Legendrian isotopies. So now instead of just smooth isotopies, if you look at Legendrian isotopies between links, you can build up a decomposable Lagrangian cobordism between those two. We have bursts of unknots, but now because we're talking about the Lagrangian or contact symplectic world, notice that if we have, say, some Legendrian knot here or link, we want to do zero handle attachments, but now it needs to be a birth of a max TB unknot. So this particular unknot, as opposed to a stabilization of it. Okay, and then the third move are pinch moves. So to see an example of that, notice that here I'm starting with the twice stabilized unknot. In this first step, I'm doing a birth of a max TB unknot, and then I'm just doing a bunch of isotopies. So basically, all I'm doing from here to here is kind of stretching out this, this portion of the unknot and moving it around. So first we're stretching it out over here, then we're gonna push it under here. But notice that we're leaving behind two of the cusps. Then we push it over here to get to the next step. And then finally we push it down here. And then this is exactly where you're seeing the pinch move. So notice that a pinch move takes two cusps and replaces them with a band in this way. So this process builds up a decomposable Lagrangian cobordism from the twice stabilized unknot to this particular Legendrian representative of the mirror of 6-1, using all of those moves. Okay, so what our theorem explicitly says, right? I gave the spoiler at the beginning that it tells us that we have Lagrangian realizations of any ribbon cobordism. Well, what it's explicitly saying is if you start with a ribbon cobordism, let's call it C, that's in 0,1 cross S3, and you have two smooth links, so it's from K0 to K1, well, then there have to be Legendrian realizations of those links. Let's call them lambda 0 and lambda 1, so that you can actually just isotope C into a decomposable Lagrangian cobordism from lambda 0 to lambda 1. And our theorem just does this by actually constructing it. So let's see how we construct this. So basically what you do first is you take your ribbon cobordism. Remember, we have a ribbon cobordism from K0 to K1, and you're going to isotope it so all of the births happen first, and then you do band moves. And we want to do band moves in kind of a nice order. Basically, we want to make sure that the order we do band attachments is always has one of the feet of the band on kind of the original component of the knot, as opposed to both of the ends of it being on knots that were birthed in the process. So that's kind of what I mean by nice order. So first, just kind of isotope your cobordism so that it has this property, and then we can just see how to build it up by thinking about the different moves in the smooth world versus in the contact symplectic world. So births in the smooth world, remember that this was, you have some knot K and you're adding an unknot separately. That's the 0 handle attachment. But over in the contact symplectic world, right, in decomposable Lagrangian cobordisms, we need to do a birth of a max TB unknot. but notice that smoothly, those will be the same moves. Isotopies, we have to be a little bit more careful. Not every isotopy of a smooth knot will just give Legendrian isotopies between any Legendrian representatives of those two knots. So you have to be a little bit careful. This is one of the places where you may see some stabilizations coming in. And then finally for band moves, basically the way you get band moves is by doing a series of Legendrian isotopies with then a pinch move. So each band move is going to require one pinch move and possibly a bunch of Legendrian isotopies. And those Legendrian isotopies may again mean that you had to have some stabilizations in there. So to see an example of kind of how this works, let's go back and look at our previous examples. So remember in the smooth world, we saw that there was a ribbon cobordism from this unknot to the mirror of 6-1. And the way it worked was we first did a birth. So we birthed this other unknot, and then we did a framed band sum. In this case, it was the blackboard framing. And so we just kind of see that there's a band going along here. Okay, so if we use the theorem to build up a Lagrangian or to see a Lagrangian cobordism that's a realization of this ribbon cobordism, what you should notice first is notice that I'm starting with a twice stabilized Legendrian representative of the unknot as opposed to the max TB one. What we're going to see is some of the isotopies that we're going to need to be able to Legendrian or Lagrangian realize this band are going to require that we had some stabilizations to work with. Basically because of these vertical tangencies. We can't have vertical tangencies in front diagrams of Legendrian knots. And so to avoid the issue of vertical tangencies, we're going to need stabilizations to kind of leave behind at the places where the band had vertical tangencies. Okay, so to see that, first we had a birth. So here we have a birth of a max TB unknot. And then to see how we get the band sum as a series of isotopies and then a pinch move, notice that we took our twice stabilized unknot, and here are our stabilizations, and I'm just going to slowly move them around to follow the path of this band. And notice that every time that there's a vertical tangency on the band, I'm leaving behind cusps that were part of the stabilization, these stabilizations we started with. And that way I'm avoiding vertical tangencies in my front diagrams. So if we look here, notice that the band first came around here. So it comes here and then goes down. Well, notice that I left behind two of the cusps there to avoid the vertical tangency issue. I'm then going to continue following this so that I push this over there. This is a perfect fine Legendrian isotopy, no stabilizations necessary. And then this pushes down through over here and then goes back to connect back up. And so notice that we would have a vertical tangency somewhere in here for our blue band. And so that's where we're seeing left behind cusps there, which were why we needed so many stabilizations to start out with. Okay, and then finally, we need to actually connect our band up with the other component, and that's where the pinch moves comes in. So the pinch move is telling us now to connect these two cusps together, thus giving us a Legendrian realization of this kind of smooth band sum. And if we look, this overall gives us a decomposable Lagrangian cobordism from this Legendrian representative of the unknot to this Legendrian representative of the mirror of 6-1. And smoothly, this is isotopic to our ribbon cobordism that we started with. So this is the idea of how the proof works, but it probably brings up some pretty immediate questions. And some of those questions are probably, well, I said that we introduced these stabilizations in the process. What is the smallest number of stabilizations that were really necessary? Did we need to have any? Or was there a way to realize that same ribbon cobordism that I gave you without the stabilizations? Or did we need that many? That's a little bit unclear to start out with. Another one is, could we actually have a max TB representative at one or both of the ends? And another one is, can you always have a max TB representative? Or there are only specific examples or examples where you can't have max TB representatives? So to start answering some of those questions, we should recall some obstructions we have to the existence of decomposable Lagrangian cobordisms. So one of the first ones was from Chantrain, which said that the Thurston-Bennigan number of the top knot minus the Thurston-Bennigan number of the bottom knot needs to be negative the Euler characteristic of that decomposable Lagrangian cobordism. And so in particular, if we're talking about the bottom knot being the unknot, well, the max TB of the unknot is -1. So that immediately tells you something about the relationship between the unknot and the TB of the unknot and the TB of the top knot. And if we restrict ourselves to concordances, that's actually telling us that in the case where the TB of our top knot has lower Thurston-Bennigan number than -1, that tells us that to have a concordance from the unknot to it, we're going to need to have a stabilized unknot at the bottom. So that immediately gives us some restrictions on what the relative Thurston-Bennigan numbers need to be. Baldwin, Lidwin, Mong then also gave obstructions using the Lawson variant. Basically, if you have the Lawson variant vanishing on one of the ends, then that gives you information about whether or not there can be a decomposable Lagrangian cobordism between the pair of knots you have. One thing to notice why this comes up and is necessary when thinking about stabilizations is that if you do a positive stabilization of a Legendrian knot, then the lambda plus Lawson variant will vanish. And obviously, if you did the negative stabilization, the lambda minus would vanish. Okay, so that tells us something about what relationship we can have between the Thurston-Bennigan numbers. But notice that our example that we've been talking about already tells us that yes, you can have one of them have max TB, because in particular, this is a Legendrian realization of the mirror of 6-1 that does have max TB for the mirror of 6-1. So it is possible to have a max Thurston-Bennigan number not on, in this case, it was on the top. So then our third question was, is it always possible to have a max Thurston-Bennigan number not on the top or the bottom? And the answer is no. There are examples we can come up with where you can have pairs of knots that don't necessarily have max TB on the top or bottom. In particular, there's a pair of Legendrian representatives of 2-3 cables of 2-3 torus knots. Because they're Legendrian representatives of the same smooth knot, they are smoothly isotopic, but Baldwin, Lidwin, Wong tells us that there can't be a decomposable Lagrangian cobordism between them. And so that tells us that we can't have the max TB ones. Okay, so we can't do that. One thing I do want to point out though is that, so I said that there are examples of pairs of knots where you do have max TB. They're actually infinite families. Rafi Walker, a senior project student with me, recently showed that there's in particular family of pretzel knots where you can find Legendrian max TB Legendrian representatives of them that you can exactly write down in this way, decomposable Lagrangian cobordism from some stabilized unknot up to them. So we even have infinite families of knots that do this. Still unknown in this case if we can find infinite families. So those are some questions that might come up for this. But there are lots of different things you could think about from this. One of them might be trying to determine if the numbers of distinct non-isotopic Legendrian kind of representatives of these Rubin cobordisms. There are lots of other things you can think about, but this is a starting place. So thanks for listening. Feel free to leave me questions or email me or come to my office hours, but see you.